A small, frozen world sitting 3 billion miles from the sun is doing something no atmosphere anywhere else in the solar system does. It's cooling itself down, actively, using nothing but the haze drifting through its own thin sky. And when scientists went looking for an explanation, they found something else entirely, a chemical signature that doesn't match any known molecule, shared between two worlds that have almost nothing else in common. Before getting into either of those findings, it's worth clearing up something the title of this video, and plenty of others like it, gets wrong. This isn't the first time James Webb has looked at Pluto. Webb's instruments became sensitive enough to study Pluto directly back in 2022, separating its faint signal from its large neighboring moon. Karen for the first time in any telescope's history. What's actually new here is what a careful analysis of that ongoing data has revealed, published across two separate studies, one in 2025 and one just this past summer, and what it found is stranger than almost anything Pluto has handed astronomers since New Horizons flew past it a decade ago. This is the real story of what James Webb has actually confirmed about Pluto, why a small dying world with barely any atmosphere at all is behaving like nothing else in the solar system, and why a signal shared with Saturn's moon Titan is now one of the more genuinely open mysteries in planetary science. To understand why any of this counts as surprising, you have to understand how little was actually known about Pluto until recently. For most of the 20th century, the largest telescopes on Earth could only resolve it as a faint, blurry point of light. Its size, its surface composition, whether it even had an atmosphere at all, remained open questions for decades, with some early estimates so far off base that they assumed Pluto needed to be significantly larger than it actually is, based on gravitational effects on Neptune, and Uranus, that later observations proved were measurement errors rather than real evidence of a massive hidden planet. Pluto held the title of ninth planet for most of a century anyway, until the International Astronomical Union voted to reclassify it as a dwarf planet in 2006, stripping it of a label astronomers had given it without ever actually having a close look at what it was. That changed in July 2015 when NASA's New Horizons spacecraft, after a 9.5-year journey across billions of miles of empty space, flew past Pluto at more than 30,000 miles per hour. It had exactly one chance, a narrow window of just a few minutes to gather as much data as possible before continuing on into the darkness of the Kuiper Belt, never to return. What it sent back rewrote almost everything scientists thought they understood. A massive, pale, heart-shaped plane stretched across the surface, smooth and strangely young-looking compared to the ancient, heavily cratered terrain surrounding it. Mountains built from water ice, frozen hard enough at Pluto's temperatures to behave more like solid rock than anything resembling ice on Earth, rose more than 10,000 feet into a thin, hazy sky. And layer after layer of blue-tinted haze extended hundreds of miles above the surface, visible even backlit by the sun. New Horizons only got that one look, though, and then it kept flying. Whatever questions its brief flyby raised would have to wait for an entirely different kind of instrument, one that didn't need to travel anywhere near Pluto to study it directly. That's exactly the role the James Webb Space Telescope was built to fill. Rather than photographing Pluto up close, Webb reads light itself, breaking it apart into individual wavelengths to reveal the precise chemical fingerprint of whatever it's observing, all from roughly 3 billion miles away. The technical challenge was substantial. Pluto and Charon sit so close together in Webb's field of view that separating their individual thermal signals had been essentially impossible with earlier generations of telescopes, which simply couldn't tell how much of any detected heat was coming from Pluto itself versus bleeding in from its unusually large companion moon sitting nearby. Webb's much larger mirror and far more sensitive infrared instruments finally solved that specific problem starting in 2022, letting researchers cleanly isolate Pluto's own signal for the first time in the history of ground and space-based astronomy. One of the first ideas researchers used that new capability to test had been sitting around, disputed and unverified for years. Back in 2017, planetary scientist Xi Zhang at the University of California, Santa Cruz, proposed something that struck many of his colleagues as backwards at the time. On Saturn's giant moon Titan, atmospheric haze traps heat and warms the world underneath it, the same basic principle that makes greenhouse gases warm Earth's own atmosphere. Zhang argued Pluto's haze might be doing the exact opposite, absorbing sunlight during the day, then radiating that energy straight back out into space as infrared heat, faster than Pluto's paper-thin atmosphere could ever hope to retain it. In effect, he proposed the haze wasn't acting like a blanket at all. It was acting like a radiator, actively bleeding heat away from a world that already had almost none to spare. At the time, there simply wasn't an instrument sensitive enough to actually test the idea. A team led by astronomer Tanguy Bertrand at the Paris Observatory finally put that hypothesis to the test using Webb's data, and the results, published in the journal Nature Astronomy in June 2025, confirmed almost exactly what Zhang had predicted 8 years earlier. Pluto's upper atmosphere really is being actively cooled by the haze particles suspended within it, and the effect turned out to be substantial, roughly 30 degrees Fahrenheit colder than earlier climate models had predicted. Zhang, whose original hypothesis had just been vindicated after nearly a decade of uncertainty, noted how unusual it is in his own field to see a prediction confirmed this cleanly, this many years after it was first proposed. Researchers now describe Pluto's atmosphere as something close to a genuinely new category of climate, one unlike anything documented. Anywhere else in the solar system where haze doesn't warm a world, it actively refrigerates one. That's the part of this story that genuinely does deserve a phrase like "shouldn't be possible," used carefully rather than as pure hype. Standard planetary science, built largely on studying atmospheres closer to home, generally treats atmospheric haze as an insulating layer, something that traps warmth the way it does on Titan, or the way greenhouse gases do here on Earth. Pluto's haze runs the physics in reverse, and researchers are still working through exactly how far the implications of that discovery extend, including whether similar hazes might be quietly shaping the climates of other distant hazy worlds like Neptune's, large moon Triton, or even offering a clue about what Earth's own atmosphere may have looked like billions of years ago, long before oxygen ever built up in our skies. There's a second discovery tied to that same haze that's quieter, but arguably just as strange once you sit with it. Even the extremely faint trickle of sunlight that reaches Pluto, roughly 1,000 times weaker than sunlight reaching Earth, is enough to break apart methane molecules high in its atmosphere. Those broken fragments don't simply disappear. They recombine into heavier compounds, forming a slow chemical cascade that eventually produces reddish-brown particles called tholins, drifting downward and settling onto the surface below. New Horizons caught early traces of this process back in 2015, and more recent observations have continued refining exactly how it unfolds. Tholins belong to the same broad family of organic molecules some scientists believe may have once rained down onto early Earth, potentially contributing raw material for the kind of chemistry that eventually led to life here. On Pluto, that same basic process has apparently been running for roughly 4 billion years, a slow, continuous snowfall of biological building blocks, landing on a surface too frozen for any of it to ever spark into something alive. That established 4 billion-year-old chemical backdrop is exactly what makes the newest findings so genuinely puzzling. While comparing Webb's infrared observations of Pluto against similar observations of Titan, two worlds that share almost nothing in common besides atmospheres built from nitrogen and methane, researchers noticed something odd sitting in both spectra. A specific absorption feature, centered around 5.11 micrometers, a wavelength where light was being blocked in a way that didn't match any molecule currently cataloged in planetary science. The finding, submitted to the journal Astronomy and Astrophysics, raised an immediate question. Titan is a large, hazy, actual lakes and seas of liquid methane on its surface. Pluto is a small, nearly airless, frozen world hundreds of millions of miles farther out. If the exact same unexplained signal shows up on both, what could possibly connect them? Researchers ran a careful check to pin down where the signal was actually coming from. By comparing light from the center of Titan's disk against light from its edges, where sunlight has to pass through more atmosphere before reaching Webb's instruments, they found the signal actually weakened toward the edges, the opposite pattern you'd expect if the absorption were happening in the atmosphere itself. That points toward the surface as the real source, frozen material sitting on the ground rather than gas drifting overhead. On Pluto, whose atmosphere is far too thin to produce a signal this strong on its own, the same logic applies even more directly. Whatever is creating this absorption is very likely sitting on the frozen surface of both worlds, not floating in the sky above either one. One candidate researchers have proposed is a family of hydrocarbon molecules called allenes, compounds known to absorb light in roughly the same part of the infrared spectrum as this mystery signal. The problem is that allenes come in many possible chemical variations, most of which have never been thoroughly studied or cataloged in laboratory settings, meaning scientists currently lack enough reference data to confidently match the signal to any specific version of the molecule. It's a plausible lead, not a confirmed identification, and researchers have been careful to describe it exactly that way. There's also a genuinely interesting difference in how the signal appears on each world that scientists are still working through. On Pluto, the absorption feature is roughly 3 times wider than the equivalent signal on Titan, even though both signals reach a similar depth, blocking somewhere between 4 and 5% of the light at that wavelength. That width difference could be telling researchers something about how the underlying compound is physically arranged, differently on each surface, shaped by each world's own distinct temperature and radiation exposure, though exactly what that difference means remains genuinely unresolved rather than something scientists have already worked out. It's worth being precise about what hasn't been established here, since it's easy for a story like this to drift into overstatement. Nobody has identified the molecule responsible for the signal. Nobody involved in this research has proposed any connection to biology, and no credible source has suggested one either. What has been established is narrower and arguably more interesting precisely because it remains unresolved. Two chemically related but physically very different worlds are sharing an infrared fingerprint that matches nothing in the existing catalog of known planetary chemistry, and figuring out exactly what's producing it is now active, ongoing research, rather than a solved case study. Researchers are currently working through additional Webb observations of Titan specifically, aiming to map exactly how the mystery compound is distributed across the moon's surface, since a clearer picture of where it does and doesn't appear could help narrow down which physical or chemical process is actually responsible. Whether a similarly detailed surface map becomes possible for Pluto, a much smaller and fainter target from Webb's vantage point, likely depends on how much additional observing time the telescope can dedicate to it. Since Webb's schedule is shared across an enormous range of competing priorities, spanning the entire observable universe, not just our own solar system's coldest, most distant corners, it's worth understanding a bit more about why Titan and Pluto, despite sitting on opposite ends of the outer solar system and looking almost nothing alike, keep turning out to share more chemistry than their appearances would suggest. Titan orbits Saturn, wrapped in an atmosphere roughly 1.5 times denser than Earth's, thick enough to support genuine weather, methane rain, and standing lakes and seas on its surface. Pluto's atmosphere, by comparison, is roughly 100,000 times thinner than Earth's, closer to a near vacuum than anything resembling real air. Despite that enormous difference in scale, both worlds run on strikingly similar underlying chemistry. Methane and nitrogen, exposed to sunlight, slowly breaking apart and recombining into heavier organic material over immense stretches of time. That shared chemical starting point is exactly why researchers didn't dismiss the matching 5.11 micrometer signal as pure coincidence the moment it turned up in both spectra. Two worlds built from similar raw ingredients, even at wildly different scales and distances from the sun, independently producing the same unexplained spectral fingerprint, is precisely the kind of pattern that suggests a genuine shared physical process rather than a statistical fluke. Pluto's unusually large companion moon, Charon, adds another layer to this same broader story. Even though it isn't the direct subject of the newest mystery signal, researchers have spent years documenting how methane escaping Pluto's thin atmosphere drifts across the roughly 12,000 miles of space separating the two worlds, where it gets captured by Charon's gravity and freezes onto its poles during multi-decade stretches of total polar darkness, a natural consequence of how the two worlds are tilted relative to each other as they orbit their shared center of mass. Once sunlight eventually returns to that part of the moon, ultraviolet radiation and cosmic rays break the frozen methane apart and reassemble the fragments into heavier reddish compounds, permanently staining Charon's poles a dark, rusty color distinct from the pale, cratered ice covering the rest of its surface. In October 2024, a separate team led by researcher Sylvia Protopapa at the Southwest Research Institute used Webb data to confirm the presence of both carbon dioxide and hydrogen peroxide frozen directly onto Charon's surface, a specific chemical combination that had never been confirmed there before, adding yet another layer of unexpected complexity to a moon whose plain, icy appearance had long suggested it should be comparatively simple and geologically unremarkable. That pattern, worlds that look on the surface like inert, frozen leftovers, turning out to host genuinely active, ongoing chemical processes once the right instrument finally gets a close enough look, extends well beyond just Pluto and Charon. Researchers have already flagged Neptune's large moon Triton, thought to share a similar icy composition, and possibly even a similar origin story to Pluto, as one obvious candidate worth checking for the same 5.11 micrometer signature, along with other large trans-Neptunian objects scattered throughout the distant, largely unexplored Kuiper Belt. If the compound responsible for this signal turns out to be common across multiple icy worlds, rather than an isolated coincidence limited to Pluto and Titan specifically, it could reshape how researchers think about the baseline chemistry present throughout that entire distant region of the solar system, an area so vast and so poorly studied that only a single spacecraft, New Horizons, has ever managed a close-up look at any part of it directly. There's also a broader technical story worth appreciating here about exactly how astronomers managed to detect something this subtle from billions of miles away in the first place. Every molecule absorbs light at specific, predictable wavelengths, determined by its own particular atomic structure, which is why breaking sunlight reflected off a distant object apart into a detailed spectrum lets scientists identify what it's made of without ever needing to physically touch it, a technique called spectroscopy that has been a foundational tool in astronomy for well over a century. Webb's infrared instruments represent a genuine leap in how faint and how precise a signal researchers can actually extract using that technique. Detecting an absorption feature that blocks only 4 or 5% of the light at one extremely narrow wavelength on an object as small and distant as Pluto simply wasn't achievable with any instrument available before Webb launched. That's precisely why this signal sat unnoticed in the original 2023 dataset for as long as it did, not because nobody was looking, but because finding it required researchers to go back and specifically examine infrared wavelengths that had received comparatively little attention in earlier passes through the same data. It's also worth stepping back to appreciate just how strange Pluto's basic physical situation actually is, because it helps explain why an atmosphere behaving this unusually shouldn't be entirely shocking, even if it wasn't predicted in advance. Sunlight reaching Pluto is roughly 1,000 times fainter than sunlight reaching Earth, meaning even high noon there would look closer to a dim twilight here. Surface temperatures generally sit somewhere between about 387 and 369 degrees below zero Fahrenheit, more than 250 degrees colder than the coldest temperature ever recorded anywhere on Earth. At those kinds of temperatures, nitrogen, the same gas that makes up most of the air in Earth's atmosphere, freezes completely solid, and water ice behaves less like the ice found in a drink and more like solid rock, hard enough in places to ring almost like metal if struck. A world running this cold, with an atmosphere this thin, was always going to behave in ways that didn't map neatly onto the physics of thicker, warmer atmospheres closer to the sun. What nobody had directly confirmed until Webb's data came back was that the specific way it diverges involves haze actively working against the small amount of warmth Pluto has left, rather than simply reducing how much of that warmth ever arrives in the first place. So here's what actually happened once the exaggerated framing gets set aside. James Webb didn't just now see Pluto for the first time, and nothing about these findings breaks the laws of physics the way a headline like "It shouldn't be possible" might suggest on its own. What Webb has actually done, patiently since 2022, is confirm that Pluto's atmosphere behaves in a way genuinely unlike anything else documented in the solar system. A haze that refrigerates rather than warms, and then, through careful ongoing analysis of that same data, turn up a chemical signature that doesn't match anything in the known catalog of solar system chemistry at all, shared by two worlds that otherwise have almost nothing in common. Pluto was stripped of its planetary status in 2006 and treated, for years, as a footnote at the edge of the solar system. What Webb keeps confirming instead is that some of the most genuinely unresolved chemistry anywhere in our cosmic neighborhood is still unfolding there in the cold and the dark, roughly 4 billion years in the making, and still, even now, not fully understood.